Good. All right. So hello, everyone. I'm Sean, and it's a pleasure to be here with you. So thanks the organizers for inviting me. And so I'm going to talk to you today a bit about kind of continue the theme of what we've been talking about this morning, about the ejection of planets from home planetary systems. And before I get going, I want to thank some people who contributed to various parts of what I'm going to show you. They're listed down there along the bottom. So here we go. Oops. Here we go. So in very simple terms, if we have a bunch of free-floating planets and we want to explain how they got there, then we want to have some idea of potential sources. And so basically, on the left here is, what's observed. You can break it down in some sort of like a Drake equation style thing in terms of maybe, some fraction of these are ejected planets. Maybe some fraction of free-floating planets are, aborted stars or brown dwarfs. And maybe I always want to leave an other category of things we haven't thought of yet, right? That's always going to be relevant. And so the idea being, in this talk, I'm going to focus on this red part, kind of the ejected planets part. And one kind of motivator for this is even in terms of other science, if we really understood this part really well, maybe then we could subtract it off of what's observed and learn something about the other parts too. Right? So learning about one part can help us with learning about other stuff as well. And so expanding on this in a tiny little bit more detail, this kind of like very simple, again, Drake style equation can kind of break down the ejected planet population into kind of simple things that we can hopefully measure or constrain. And so just to put some numbers on here. So this F giant would be kind of the occurrence of planets that are capable of ejecting the planets that we see that are free floating. Right? So we need to know that number. We want to know the fraction of systems that go unstable. And I'll talk about what I mean by unstable in a little bit. Basically, unstable such that orbits cross each other and ejections can happen. And then the number of planets ejected anytime that happens. And of course, the kind of key underlying premise here is that for every ejected free-floating planet, there's a corresponding exoplanet with equal or higher mass because it ejected. And so that's kind of the idea. That's where we're going. And so in some sense, we're going to go from planetary systems to free-floating planets with a little bit about wide orbit planets. And so that's what I'm going to talk about. And the kind of the common thread here is dynamical instability. And so this is similar to the cartoon that Ida-san showed. And so we're going to get a lot more into what's going on here in a minute. So to start off, I'll focus on the solar system. I'll talk about kind of three phases of dynamical instability of the solar system. And they're kind of generalizable to some degree anyway. The first phase is not really what we usually would call dynamical instability. It's more just kind of growth. And so what does dynamical instability mean anyway? I kind of like to think about it as being anytime the orbits of two objects are crossing. And then, what happens next? So things are unstable, something's going to happen next. And so in very simple terms, if a bunch of planetesimals or planets or whatever are on perfectly concentric orbits around a star, then it's nice and stable. But as soon as things cross, then something's going to happen. So in the early phases of planetary growth, when this happens, when there's a bunch of planetesimals or whatever you want orbiting a star, to grow at all, this has to happen because the orbits of things have to cross so that they can bash into each other and grow. Okay, so like I said, this is not really what we consider dynamical instability usually, but technically it's still a dynamical instability phase. And so the key thing here is that, early on, this kind of thing happens where orbits cross and it leads to growth. But later on, we're going to talk about orbits crossing and it leads to ejection. So what's the difference? Why does growth happen sometimes and ejection happen other times? And so to kind of think about that, there's kind of a very simple way to conceptualize it. And so imagine a planet orbiting a star. And then this dashed line is, some little asteroid or something orbiting the same star. You can say, well, what, can this planet eject the asteroid or not? And this has been kind of explained a little bit this morning, but I'll go into a little bit more detail here. Well, it can eject the asteroid if the impulse, kind of the change in velocity that the planet can give to the asteroid is bigger than the escape speed from the star, right? And so in really simple terms, the requirement for ejection, at least in one encounter, is that the escape speed from the planet's surface has to be bigger than the escape speed from the star at that distance. And the reason it's the escape speed from the planet's surface is just because that's the biggest, velocity kick that a planet can get. And so these two quantities, the escape speed from a planet's surface and the escape speed from the star at that distance are kind of the two key quantities in terms of what controls ejection versus growth. Okay, and that number, that ratio is often called the Safronov number because it was first come up with by Viktor Safronov back in the 60s. And so there's this really simple thing. It's often called theta or theta squared because then you can get rid of some square roots. So people like to square it because square roots suck. And so there you go. All right. So it's really simple. It's just the ratio of the escape speed from a planet's surface, the escape speed from the star at that distance. And you can kind of formalize it like that if you want. So you can see that for Jupiter, this is the setup for Jupiter. For Jupiter, theta is about 3. Okay? And so theta squared is about 2. And it scales with these parameters like that. And so in very simple terms, again, a high Safronov number means the escape speed from the planet's surface is really big compared to the escape speed from the star. So scattering is favored. It's easy to eject things. Safronov number is low. That means the escape speed is low, and things tend to wind up colliding rather than scattering and ejecting. And you can draw this out. I made this little plot last night. So this is analogous to a plot that Eve showed earlier. Basically, these are curves, separating the Safronov equals 1. Basically these are Safronov equals 1 curves for 2 different densities of planets. Okay, so basically in the upper right, it's easy to eject things, and the lower left, it's hard to eject things. And so you end up having accretion rather than scattering. And so for scale, right, this is kind of interesting to note, right? Orbital distance on the x-axis. So the Earth, right, the Earth at 1 AU is going to collide with other stuff. It can't eject anything. But the Earth out at, 50 AU can eject stuff. Likewise, Jupiter, up here at a few hundred, Jupiter ejects a lot of stuff from the solar system. A hot Jupiter cannot eject. These are very simple scaling, but it's important to have in mind because this is what controls the dynamics of scattering, which is what controls the dynamics of what gets ejected. So moving on to the first, the first real instability, in quotes, in the solar system. And this probably happened in terms of the accretion of the ice giants. So the current best model that I'm aware of anyway for the accretion of the ice giants is that Jupiter and Saturn, these big black things, formed first, and there was a population of icy cores further out that were migrating inward, and they wanted to keep going, but they were blocked by Jupiter and Saturn, whose orbits were more or less stationary. All right, and so they migrated inward, and their orbits kind of got squished, and they grew. And so here's an animation of that process happening. One more time. So basically, these things are moving inward. The color indicates their mass. And anytime they get way up here, that's something getting ejected. And so at the end of this kind of simulation, we're going to end up with a few different ice giants that formed, in this case, 3. And these are great inputs to the next phase of instability. And what's important in terms of free-floating planets is the kind of the byproduct of this process is a bunch of mass got ejected. About half of the mass in these objects was kicked out, and the other half ended up in the ice giants. And this is the only model that I'm aware of that can match basically what we see. It can match the ice giants really well in terms of their masses, their mass ratios, and the fact that their spin axes are very tilted. And we think that requires several giant collisions to explain. And like I showed, so this is not the present day solar system. There's one more instability that happened. The one that's usually called the giant planet instability, or sometimes the Nice model. That was the first incarnation of it. And so the initial conditions of this are basically, these are the orbits of the 5 different giant planets, one of which is going to be removed. And the green dots are outer planetesimals, kind of like primordial comets. And we think there's maybe 20 Earth masses in this primordial disk of outer comets out there. And so the instability itself looks something like this. This is countdown to instability in the top right. It happens pretty quick, and boom, when the giant planet's orbits go unstable, one of the ice giants was ejected, the planet's orbits spread out, and they end up on basically their current values. And this model is really appealing. I often give long talks on it, why we like this model. The reason is that it can explain a bunch of small body populations in the solar system, as well as the orbits of the giant planets. So if you want more details about that, we can talk about it. It was initially conceived as kind of a delayed instability, but recently that argument has changed. And so the concept, if you ever heard of it, of the late heavy bombardment has disappeared. So that doesn't exist anymore. And so now we think this instability still happened, but it happened much earlier. And I had a whole slide explaining that, but it was going to take tons of time. So I took it out. But I have it in the extra slides if anyone wants to know more. And so in terms of a mass budget, right, how much stuff got kicked out of the solar system? Well, based on these kind of two phases of instability, we think that something like 20 Earth masses and planetesimals got ejected, including, based on a question yesterday, maybe 1,000 Plutos or so. And maybe 5 or so planets got kicked out, a few super Earths during the growth of the ice giants, and that extra ice giant as well during the other instability. So that's kind of the mass budget of what we think the solar system kicked out. Now moving on to exoplanet systems. So here are the known giant exoplanets as of a few years ago. So the cutoff I used here is about 30 Jupiter masses or so. Excuse me. And so what you can see here, right, this is orbital eccentricity, a little diagram for what each shape means on the top left, versus semi-major axis. And Jupiter is the only planet of the solar system that's detectable right now. So I threw it in there as well. And so as you can see, there's this broad eccentricity distribution among giant planets. There's a clump of hot Jupiters down here. And there you go, right? And so we think that kind of two processes were really central in shaping this distribution. One being orbital migration, which is generally thought of as being inward, but not universally so. And the other being planet-planet scattering. And so what is planet-planet scattering? We've heard about it a little bit. Let me show you an animation of it next. And so this is the idea that anytime a giant planet forms, it probably doesn't form in isolation, but the planets probably form on relatively circular orbits, but they don't stay circular forever, right? They kick each other around, change shape, and once their orbits cross, it's dynamical instability and crazy things can happen. And so here's an animation of one such thing that was made by Eric Ford. I love this movie. So here's 3 kind of super Jupiters orbiting a star. The outer 2 now have orbits that cross. And what you can see is when they get really close to each other, they have a series of close gravitational encounters where they exchange orbital energy. And at the very end, one of them gets a big kick and gets launched out, never to return again. And the surviving planet has this stretched out eccentric orbit. And so in some sense, its eccentric orbit is kind of like a scar from this violent past. I love saying that. It's very dramatic. All right, anyhow. So remember, what controls this, right, scattering versus, accretion is the Safronov number. And in a really cool paper by Ford and Razio back in 2008, they showed that the eccentricities of observed exoplanets correlate pretty strongly with the Safronov number, right, or as well as we can determine it. And so past, for large Safronov numbers, there's much higher eccentricities because scattering was more prevalent than for low ones. That's pretty cool, right? So this whole story fits together pretty well. All right, and another reason that we like this general planet-planet scattering in quotes model is that it matches the eccentricity distribution really easily. And so here is kind of a cumulative distribution of observations versus very simple simulations. And the only caveat here is to match this distribution, it's required that a large fraction, at least 3/4, maybe more like 90 or 95% of all giant exoplanet systems that we see are the survivors of instability, right? So they all have those scars that are so dramatic, right? And so, but if we assume that, then we can match everything really nicely. There is another kind of part that's a little tricky and that matters, especially when we talk about rogue planets, that's the masses. And so it turns out that the eccentricities of giant exoplanets correlate with their mass in a way that's not obvious. And so first, just concentrate on the gray curves here, okay? So what I've done now is just taken the distribution of giant exoplanets and chopped it into 2 mass bins at one Jupiter mass. So the high mass ones are the dash line. I always screw that up. The dash line, and the lower mass ones are the solid line, okay? And so what do we see? We see that the high mass ones have higher eccentricities than the low mass one. All right, now, before you even look at the simulations, I should have these up here. Anyhow, before you look at the simulations, right, if you have a bunch of different mass planets orbiting a star, they scatter each other. There's sort of this equipartition of energy kind of thing that we all learned about, right? So the lower mass ones should have higher random velocities, which means they should have higher eccentricities than the higher mass ones. And that's the exact opposite of what we see, right? These are great fits. The simulations are great fits, but they're reversed. They're exactly wrong. And so this is weird, right? Why should this be the case? And you can actually explain it in a pretty intuitive way, which is that you don't start off with a kind of even mix of planets in a given system. Rather, within any given system, the masses are correlated. So a high mass disk will form a bunch of high mass planets. a low mass disk will form a bunch of low mass. And if you assume that, it works out really well. And that outcome can even come naturally out of formation models, as shown by Ida et al. 2013. Okay. So in the end, it still works. We can still match everything we see with this planet-planet scattering model. And in terms of how many planets might be ejected during each instability, can easily just do a bunch of this type of simulation of planet-planet scattering, increasing the initial number of giant planets. And you can see the more giant planets start off, then the higher fraction of them get ejected. Right? That's this blue curve is the fraction of planets that are ejected as a function. So if each system really formed 50 Jupiters, then you're ejecting a whole lot of them. But basically, the simple take-home message is that in general, this mechanism ejects at least one planet at a time, one planet per instability, but it could be even more in systems that form a lot of giant planets. And of course, they don't only eject giant planets. And so I'll start this movie because it takes a little while. So in real systems, there's more than just the giant planets. Here's a simple system where there's a bunch of rocky stuff that's trying to form terrestrial planets here. There's 3 giant planets, and then further, those blue dots, those are all kind of cometary planetesimals that are bashing into each other and producing a debris disk whose properties I calculated, but you don't care about here. And then this movie slows down because, boom, right? That's a dynamical instability that happened among the giant planets. And the giant planets dominate by mass, and so they throw all this other stuff all over the place. All the other small stuff are just kind of like innocent bystanders. And so a lot of that rocky stuff got dumped on the star, but some of it was ejected. All of the outer planetesimals were ejected. Right? So in the end, in this particular system, we end up with kind of giant planets with pretty eccentric orbits, similar to what we see around many stars. And a bunch of stuff got ejected. So what actually got ejected? In this case, about 5 rocky planets, 20 Earth masses in planetesimals, and 1 gas jet got ejected. And I know we're talking about, rogue planets here, but of course, once in a while, the rogue planetesimals can pass through the solar system as well. So we know of 2 interstellar objects, Borisov and Oumuamua, of course, that have passed through the solar system. And the Rubin telescope should find a bunch more. So that's the other end of this mass spectrum of this kind of interstellar object. And in terms of the mass budget of bodies ejected from exoplanet systems, like I said, each instability ejects usually at least 1 planet of similar mass, and then a bunch of smaller mass stuff, lower mass stuff like planetesimals and lower mass planets as well. And so it's interesting to look at every one of these dots, especially the ones at high eccentricity. Each one of those is ejecting some planet to get to where it's at right now, right? So in the full story, you don't become a very eccentric planet without having ejected something in the process. And another point is that the ejected population really depends on the occurrence rate of planets with this large Safronov number. Right? And so here's a cool graph by Laughlin and Batigan. And what they've done is basically taken the exoplanet population from a few years ago, and they colored it by Safronov number, more or less. So the red ones can eject things, and the blue ones can't. And so what do you see? Basically, super Earths down here, they can't eject anything. They're too small, too close in. Hot Jupiters can't eject anything, but the outer, cold Jupiters can. And so, like I was saying, what's missing is this stuff further out. And this has been pointed out in other talks previously today. Right? These planets, ice giants at 10 AU or further out. These planets have enough gravity that they can eject stuff too. They can't eject the free-floating planets that are a Jupiter mass, but they can eject free-floating planets that are an Earth mass. And so they matter a lot in terms of the microlensing observations of free-floating planets especially. And so going back to what I was talking about at the start, these kind of different factors. So now we know that basically pretty much all systems go unstable. That's the second one. I'm jumping ahead of myself. So we want to know F giant better, right? The fraction of systems, the occurrence rate of planets that can do the ejecting. That's an observational question. We think based on matching observations that pretty much all systems go unstable, and all systems eject at least 1 planet per instability. And so this has been applied, this kind of reasoning was applied to a sample of free-floating planets from direct imaging by Mirik Roy et al. In 2022, and found that based on the occurrence rates of planets in the right mass range, right, at least 4 Jupiter masses in this case, ejected planets could explain basically between 10% and 100% of the sample. right? And the uncertainty comes mainly from uncertainties in that parameter F giant, like exactly how many of those planets are known. All right, that's good time. All right, so now I'm going to transition a little bit and talk a little bit about the spatial context of ejection and the fact that stars obviously form in clusters, and those clusters don't last forever, but they make really pretty pictures, of course. So what happens if a planetary system goes unstable while the cluster is still there? So this is an animation, an awesome animation made by Andre Isidoro, based on a paper that he started when he was a postdoc with me like 8 years ago. And it's finally going to happen. I think it's really going to come out one of these days. But anyhow, the animation is here, and that's what counts. So there's a bunch of panels. In the bottom right is the kind of parameter space view of the one that we're going to show here is the solar system instability. Okay, the instability number 3. They're centered around the sun, which is at the origin in the plot on the left, and in the top right is kind of a physical view panel of the system. All right, so the instability is not quite triggered yet. It's about to start in a sec. There we go. So you can see this ice giant here. Oh, I can't see it. Anyhow, this ice giant here is the one that's in the process of getting ejected, gets kicked to a higher and higher semi-major axis, very high eccentricity. Once it gets to 1, it'll be gone, but it never quite gets to 1 because it's on this wide orbit. And then other stars fly by and change its orbit and lift its perihelion by decreasing its eccentricity, protecting it from getting ejected next time. But the whole cluster is evolving and things are moving around. And you can see this, the speed moves, so we can see each encounter that happens. There's another one. You can see its orbit change dramatically there. And I love how you can see the cluster sloshing around and stuff. Anyhow, you can see basically once it's on a wide enough orbit, the flybys from stars matter, and some fraction of ejected planets never make it to being ejected. They get stranded on these very wide orbits. So the initial goal of this paper was to explain Planet 9 if it exists. And we found that you can trap a planet on orbit like Planet 9 at least some fraction of the time. Right, so this is a pretty good Planet 9 analog. Semi-major axis of about 500 AU, eccentricity of about 0.5. But the trapping efficiency depends on various parameters related to the cluster and also to the planets that are doing the scattering. So this plot's kind of busy, but the key thing is the trapping efficiency on the y-axis for solar system-like things, the two rightmost parts are basically like 5 to 10% or so. All right, and they're very low for a couple of other things. And so let me just kind of explain intuitively why that is. So scattering in kind of solar system-like systems, the actual ejection process is more or less like this. So, our ejected ice giant's in orbit like this, gets kicked by Jupiter, gets kicked by Jupiter again, and basically it only needs a few more kicks until it's gone. Right? But in the process, a star comes by, lifts the pericenter by dropping the eccentricity a little bit, and it gets stranded. But if the same process happens in systems with many Jupiters, or the same applies to circumbinary stars, circumbinary systems, basically the kicks are too strong. And so the kick number 2, the star, basically the planet's gone. And so there's no time. There's not a long enough time window for there to be a significant probability of a star passing by to do that. And then the opposite is true in systems that only have ice giants. They're scattering and they kind of keep kicking to higher and higher eccentricity. But the scattering phase is too slow. It takes too long to get to really wide orbits where the external perturbations matter. And so in the end, those factors explain that trapping efficiency plot with all the dots everywhere. And finally, one last thing to note is that after the cluster is gone, instabilities that happen can still lead to some trapped planets. And then it's not because of being in a cluster, it's just kind of being in a field. And there's external perturbations that are acting on the solar system all the time related to the galactic tide. The galactic tide is basically small changes related to the fact that the density in the galaxy is not perfectly smooth. The key one comes from the vertical gradient in density, if you care. And then there's also some stars that fly by as well. So this example is showing an instability among a 4 giant planet system, and that gray planet, which is about a Saturn mass, gets kicked out and it's almost ejected, and it stays on this wide orbit long enough that the galactic tide shrinks its eccentricity and traps it out there with an orbital separation that's the same. It's basically in the Oort cloud. This is how Oort cloud comets get there too. And so It gets trapped out there at 50,000 AU or so. And you can see it survives for at least 1 billion years. So this kind of thing can happen too. The odds of this kind of thing being captured are smaller, maybe like 5%, but so be it. All right, so that's good time. So let me just kind of summarize the key points. First one being that the giant exoplanet eccentricities, they're kind of a direct link with free-floating planets via dynamical instabilities, planet-planet scattering. And so it's a nice way to anchor, these theoretical models to free-floating planets. A key kind of missing link is the census of exoplanets that can eject the observed population of free-floating planets. And this is key, especially going to lower mass ones, such as with the microlensing technique. And just this last part that I mentioned, that this kind of simulation predicts that at least 1 in 1,000 stars or so should have one of these very wide planets, like a Planet 9 type planet. And exactly the orbit it has will depend on the timing of instability. And I'll stop there, but I'll leave you a little animation from my blog in case you're interested. All right, I'll stop there. Thank you.
On top. All right, so questions for Sean.
Okay, so this is buried in your talk, but I was wondering if you could give me a 1 or 2 sentence condensed version. One of the things about microlensing that makes it unique is that it's sensitive to actual analogs of our ice giants. So what would you say is the main, the frequency and mass function of ice giants, things beyond 10 AU? What are they mainly diagnostic of? What part of planet formation are they giving us a handle on?
So if you find ice giants at 10 AU, what does it mean? Like
10 or 20 or 30 AU, what is that? In our solar system, I kind of see in the model that you predict, you showed what that's telling us about they form, migrated in, dynamic instability, push them back out. Is that generally what you're predicting for other planetary systems?
Yeah, I suppose. So yeah, I guess finding the frequency of ice giants out there would tell you something about kind of basically how frequently cores of that mass form far away and survive out there. Versus, what's the alternatives? Either they don't form out there or they form really fast and they migrate out of the way really quickly. And so both of those are important in terms of kind of the general picture. So if you found a very high frequency of ice giants out at 10, 20, 30 AU, it tells you a lot. It tells you something, a key ingredient, because if your model predicts that nothing forms there or that nothing stays there, it doesn't work.
Other questions?
In your simulation of the solar system, like instability embedded in the cluster, we saw the various planets coming by perturbing that one centric planet. It looked a bit like a random walk, like successive flybys for each. But I always sort of imagined it more like a lazy flight, there is one strong encounter that really handles the most. What is it?
Oh, good question. So in that case, you're right. There was no really strong flyby. And I think the reason is that in cases where there's a really strong flyby, the planet's ejected and you don't see it. And the example we chose is one where you end up with planet out there, because that's what I was trying to illustrate in the talk. But the capture rate is never more than 10%, right? So I'm showing you kind of a relatively rare outcome to illustrate that particular branch of possibilities. More likely there's either, if no star flies by soon enough, then the planet will just be ejected. If a really strong flyby happens, then it ejects also. And so I'm showing the case that does not have the dominant one, which is not the most likely outcome, admittedly.
Other questions?
So you say 10 to minus 3 wide orbit planets because of the perturbation. And what about the case for the dynamical instability? How much fraction of them are in the wide orbit?
Oh, okay. So I would have to look at the paper to get all the numbers exactly. So like I said, the trapping efficiency here can be as high as about 10%. But when you put it, this 10 to the minus 3 includes, trying to include factors related to the occurrence of that type of system, right? And so we end up with some number that's 10 to the minus 3. The trapping efficiency later, in Oort cloud type orbits, at least from what I've done before, never gets above about 10%. It's usually a bit lower. 5% or even lower. And so that's the trapping efficiency you get per instability. And so the actual occurrence rate is smaller. It's maybe 1 per few thousand stars.
Any other questions? Jeremy? No.
I was wondering if you look at the inclination, talk about the electricity, but there, I guess your simulation with one of this spark cluster. Do you get any probability of inclination?
Oh yeah, sure. I mean, so the inclinations get excited during scattering very strongly as well. There's not, I don't use it to anchor anything down because there's very little in terms of constraints. There are for hot Jupiters, of course, with the Roster-Milk-Laughlin effect, the obliquity measurements of the star. That's a whole nother ballgame because then you have to add in tides, star-planet tides, which would do the capturing, once planets are in very eccentric orbits. And so that's a whole other realm, but it's consistent with the general scattering frame.
Sam, do you have a question?
Like the big bombardment backup slip.
Oh, you want me to bust that? All right. Oh, wait. All right. So what do I got here? This is explaining why we like the instability if you want. Oh, all right. This is going to take a minute, though. You okay for that? All right. All right. Anyhow, so the I have to put myself in solar system formation mode. Okay. So basically, if we agree that an instability, a dynamical instability happened in the solar system, when did it happen? All right. The general thinking, based on Apollo samples, a bunch of scientists in 1974 at Caltech came up with a concept called the terminal lunar cataclysm. It was based on Apollo samples that were sampled here, from actually people walking around on the moon and gathering rocks and bringing them back. Right. And so what does this look like? Basically, look at this lower curve, the one that has the big spike that says cataclysm. Right. That was the framework developed by Terra and others starting in the 70s. And so this was done basically age dating different rocks taken from different parts of the moon. And the initial Nice model dynamical instability was kind of anchored to this. And so basically the idea from the original dynamical instability model for the solar system was that, well, we can explain a bunch of stuff bashing in the moon at a given time if the solar system formed in a slightly more compact configuration, then it stayed there and waited about 500 million years, and then it went unstable. It can match this spike, right? This is the idea proposed by Gomez et al. 2005. And so in this idea, basically, the dynamical instability happened right there, and that's when there's a giant bombardment of asteroids and comets in the inner solar system. Right? But the recent analyses, there's a bunch of reanalysis of this stuff, and it's almost certain that there's a sampling bias in the Apollo samples, and that even though they're taken from different places, they're all sampling surface layers that were ejected from the same impact, Imbrium basin forming impact, basically. And so one giant impact happened at 3.9 billion years, the Imbrium basin forming impacts. It contaminated a large fraction of the surface. That's where we have rocks from. And maybe I should stop there because there's even more little bullets that are going to show up that you probably don't want to hear now. But it's a big story, and it's key for understanding the solar system. And the timing is key also for, did the instability happen while the sun was in the cluster or not? If it's late, then the cluster's gone. If it's early, the cluster's still there, and that affects the dynamics and so on. But I'll stop.